In this part of video 2, we're going to discuss entropy, free energy, and equilibrium, continuing from last time where we discussed internal energy and enthalpy. Okay, so let's start by considering a very simple reaction. Two single strands of DNA that come together to form a base pair helix. So we can measure all of these. We can measure the delta H of the reaction. Let's say it's large, it's negative. We know from our previous discussion of forces that there are various interactions that are going to stabilize this, like hydrogen bonds and van der Waals interactions and so forth. But the enthalpy change for the universe is 0, so that can't be driving that change, even if with all these favorable energies that are occurring, that can't be driving this. So what's determining the direction of the reaction? And that is entropy. So we'll first look at entropy in a statistical sense, and this is the famous formula for entropy is Boltzmann's constant, Boltzmann's formula, and it's Boltzmann's constant times the log of the statistical weight of a distribution. That weight is given if you have n particles, each of which has a particular energy level. So the jth particle has an energy level J. It's given by this formula of n factorial divided by the product over all of the particles, the number of particles in a given energy level, factorial. So let's look at an example to make this clear. So let's just take 5 particles that we can distinguish, and we're not going to worry about this. There's an important, in statistical mechanics, there's a very important distinction between distinguishable and non-distinguishable particles, but we'll ignore that here. So let's just take 5 particles. And what's the most probable distribution that those particles are going to be over 5 equally spaced energy levels, okay, with a total energy constant? Okay, so here's our little energy level diagram. We have 5 levels. We can put all of them into one level, okay, and then we can compute this weighting term. And it'll be 5 factorial. There'll be none in the first 2 levels. So 0 factorial, remember 0 factorial is 1. 0 factorial times 5 factorial, 0 factorial, 0 factorial. So that weight is 1. Let's think about another distribution. We'll put one particle each into each of the levels, okay? Now we'll have 5 factorial divided by 1 factorial there, and that's 120. So you can see that this is a much more probable distribution than this, okay? There's more ways of arranging the particles than in this configuration. Another way of saying is that there are more substates. There are more ways of arranging the particles in different in these different energy levels, and those are referred to as substates. And this is really this linkage of entropy. You've all heard of entropy as disorder, and really what it means, it's a higher entropy, a higher state of entropy means you have a higher probability of that particular distribution of energies, of energy states, given a total constraint on the energy. Now, this is the statistical view and really the right way to think about entropy. But of course, again, thermodynamically, entropy in a much more abstract way can be thought of it in terms of bulk properties, bulk changes in solution. And the thermodynamic definition of entropy looks a little weird, okay? Entropy is denoted S, so the change in entropy for a reaction is going to be the heat absorbed by the system in a reversible process divided by the absolute temperature. And so its units are joules per mole. That's, that's a molar heat divided by temperature. Okay, now this is a very weird looking equation at some level. So how does this relate to this statistical view as a measure of probability? So again, larger S means that W term is larger, you have, it's a measure of probability, higher entropy. So how does this relate? Well, if you look at the equation, you just get an intuitive feel for this. It's the ratio of a randomizing influence. Remember, heat applied to a system, if it raises the temperature, there's more thermal motion, there's more random motion, and it's the ratio of that heat added to the temperature, and the temperature is a reflection of how much randomness is already present. Higher temperature, remember we saw you have a bigger distribution over these different over fixed energy levels, so it's basically that ratio. Okay, so Q, again, the heat is a disordered form of energy, random motion. Okay, so S should be proportional to that. Now the temperature term in the denominator, if you have, imagine having something at a given temperature, you now add heat to it, more states get populated, okay? More configurations become available. That's another way of saying it, because it's easier to move between, the distribution will change to populate higher energy states. But that number of states that's populated initially will depend on T. So at very low temperatures, like we saw before in the previous video, very few states are populated. So if you add heat to that situation, you're going to have a larger effect on the randomness than adding it to a system that's already very highly distributed over a number of states. So just from that simple argument, you can see that the entropy should be inversely proportional to the temperature. Now, it turns out, and this is a subtlety we don't need to go into, you can go back to your basic thermodynamics books, that the entropy needs to be a state function. We talked about enthalpy and internal energy being state functions. It's path independent. The delta E or delta H is independent of the path that you took to do that. It's the same story for S. We want it to be a state function also. It doesn't matter what the path is for the change in the reaction. And it turns out we need to have the so-called reversible heat applied, which is basically means that heat is applied as successive infinitesimal changes. Or another way of saying it, it's kind of applied in a controlled and not arbitrary way. So this is a subtlety you can go and read about, but that's why this Q reversible is there. Now, the second law of thermodynamics says that the entropy of the universe increases for a spontaneous process. And all that means is that the universe is always moving from an ordered to a disordered form of energy, or really, in terms of thinking about it statistically, from a lower to a higher probability state. Okay, so this is what really drives the direction of reactions, chemical reactions in the case we're going to be focusing on in this class mostly. So the change in entropy of the universe is always greater than zero for a spontaneous process. You're always going to want low to high probability. Now that change in entropy, of course, of the universe, remember the thermodynamics, we break the universe into the system we're studying and the surroundings. So again, that says that the change in the entropy of the system plus the change in the entropy of the surroundings has to be greater than zero. Okay, so we have that. Now, that tells us that the change in entropy of the universe determines the direction of the process. But of course, practically, we're not measuring the change in the universe. We want to focus on the system we're studying. And this is where the concept of free energy comes in. So let's think about the system plus the surroundings, and they're at the same temperature. So in some process, let's say a chemical reaction, we're going to transfer an amount of heat to the surroundings. We'll call it Q surroundings here. Now, the change in heat of the surroundings, where at thermal equilibrium, is minus the change in heat in the system. Doesn't matter if this is absorbed or given off by the system, but they are negative. They're of opposite sign. that means that the overall entropy change of the universe you can now write as change in entropy of the system, and now we'll use our thermodynamic definition of entropy. That will be Q surroundings divided by the temperature of the surroundings. We can now, because the Q surrounding equals minus Q of the system, and the temperature of the system and surrounding is the same, we now have delta S for the system, the change entropy of the system, minus Q system divided by temperature of the system. And look what we've done here. We've now got the whole entropy change, the entropy change of the universe, which is what is driving the process, but it's now completely described in terms of the system. Okay? Now, if heat is lost from the system at constant pressure or gain, doesn't matter, then that's going to be, by definition of enthalpy, delta H. So delta S system, this part of the equation here, delta S system minus Q system divided by T is delta H over T, and that has to be greater than 0. That's the second law. Okay, so now everything has been described in terms of the system, and we define the free energy as G equals enthalpy minus T times the temperature times the entropy. Okay, and so for a change, for a process that is spontaneous, that means that delta G, the change in this quantity, change in free energy, has to be less than 0. Okay, and this is delta G is the change in free energy, and that's what we normally work with to decide if a process is spontaneous. Now, again, just to emphasize this, the driving force for spontaneous change is the change in entropy of the universe. That has to be greater than 0. And maximizing this is achieved, if you look at the equation here, by the system entropy change, the sum of the system entropy change, how much its randomness changes, and the amount of enthalpy or heat you can think of that's pumped into the surroundings. So delta G is delta H minus T delta S. That's for, again, a constant pressure and temperature process. We're talking about enthalpy here in solution biochemistry typically. Okay, and again, systems, if you look at the free energy, they tend to a minimum of free energy, not the total energy. So remember when we looked at the internal energy of a molecule with balls and springs, we were talking about the lowest energy point, let's say, of a bond on a spring, and that would be the equilibrium position of the spring. When you think about the whole system and all the different microstates of the system, the system or the change in chemical reaction, whatever, that tends toward a minimum of free energy, not the total energy. So really, the free energy is really the quantity we have to focus on. And again, it's negative for a favorable change. It's positive for an unfavorable change. So really, the way to think about free energy is that it's a way to account for the total entropy change of the universe, the system and the surroundings, but focusing on the system. And it's essentially giving us the amount of energy that's available to do work, given that the entropy of change in the universe has to increase. Or a way to think of it is that you lose useful energy to heat. Okay, and this is why you never have perfectly efficient processes, and you learn about steam engines and so forth, and that's really the concept. Okay. Now you'll remember that free energy is very closely related to equilibrium. So if we have a simple reaction, A is in equilibrium with B, the equilibrium constant is going to be concentration of B divided by the concentration of A, and that equals e to the minus delta G over RT. Or rearranging that, delta G is minus RT log K, and that, of course, equals delta H minus T delta S. Those are just the definitions. Now, this difference in energy between This is very important to remember, because what you'll see in many of the papers we're going to look at is that we're often comparing, let's say, a wild type and a mutant protein. So let's say we have a wild type and a mutant protein P binding to ligand L. So we have an equilibrium you can write down as the wild type protein plus the ligand forms this bound state. Delta G will be minus RT. Let's say we measure that equilibrium constant. Delta G is minus RT log K. And then we have the mutant binding, and that will be some different different equilibrium constant that we can measure. And its free energy change is going to be then delta G mutant equals minus RT log K of the mutant. So the difference in free energy between the wild type and the mutant protein, which tells us something about what that mutation did in terms of perturbing the reaction, is going to be delta delta G, the delta G wild type minus the delta G mutant. Okay? And of course, that is very simple to get experimentally, because we measure these two equilibrium constants, and if we just work through the equation minus RT log K minus RT log K, it's just the log of the ratios of the equilibrium constants. Now, this is very important to think about in terms of scales. This is something that often isn't appreciated. Remember, the gas constant is about 2 kcal per mole Kelvin. Temperature, room temperature is 298, let's say. So let's say we have a 10-fold change in equilibrium constant. Okay, that ratio is 10. Okay, but this is a logarithmic function. So the change in free energy corresponding to a 10-fold change, which can be quite substantial and significant in biochemistry, is only about a kcal per mole, about 1.4 kcals per mole. It's a very important number to remember. A 10-fold change in equilibrium constant is about 1.4 kcals per mole. These are really not very big energies. We talked about, well, we'll talk about hydrogen bonds and some of the non-covalent forces, and they were all on this order or even smaller. Okay, so the changes we look at in biochemistry are very, very subtle energetic changes. Okay, we're not talking about breaking covalent bonds typically. I mean, in some cases we are, but in enzymes. But a lot of times, let's say for protein-protein interactions, we're really talking about extremely subtle differences in energy. Now, delta G, delta H, and delta S are these state functions which we've mentioned a few times, that they're independent of the path of how you got there. And this is very important in analyzing certain biochemical reactions. For example, let's imagine, and this is sort of a preview of allostery that we'll be talking about later on in a couple of weeks in the class. Okay, so imagine you're having a macromolecule that binds a ligand, okay, with some affinity, so some equilibrium constant, okay, and that, in an abstract sense, we won't talk about mechanism here, that complex allows the macromolecule to change conformation to M star, and there's some equilibrium associated with that change of conformation. Now, we can also think about it that the macromolecule itself could be in equilibrium with this other state, M star, and that binds the ligand. Then, let's say this promotes ligand binding so that the ligand binds more easily, so this equilibrium is more favored. Okay, this is a very typical kind of analysis. So in this red path here going this way, we would say binding promotes a conformational change. Now the blue path going this way, conformational change promotes binding. So we change conformation, that makes binding more easily. Okay. Now the delta G going from M to M star L has to be the same. Okay, it's a state function. It's independent of the path. So if we write down the delta G for path 1, it's going to be minus RT log K1 minus RT log K2, and that has to equal going this way. Okay. So if we rearrange everything, we can see that the ratio of K4 to K1 has to equal K2 over K3, and that's in the allostery business called a coupling factor. So if that coupling factor is greater than 1, it means that the binding promotes conformational change. It's favoring this M star L, or conformational change is promoting binding. Now, you can't tell the mechanism from this thermodynamically, okay? But this coupling factor is very useful for saying, is it a positive or negative allosteric regulator? But we can't tell mechanism from this, and this is where thinking more molecularly, and we'll be going through this later in the class, comes in. But the point about these state functions is that you can look at processes through these different paths, and that turns out, as we'll see in some papers, very helpful. Okay, now how do we interpret, if we measure an equilibrium constant, let's say for our little reaction here, how do we interpret the contributions of these terms, of delta H and delta S? Well, H is a measure of internal energy, okay? So you can try to account for these changes in the various energy terms. For example, you form hydrogen bonds between two nucleotides, that's favorable. But each of these unpaired nucleotides could be forming hydrogen bonds with water. Now, they may be, it may be that if you're in a somewhat lower dielectric environment, for example, there are people who claim that that would be favorable. But you have to think about, all these contributions to energy on both sides of the equations. Remember, you're always looking at differences. Okay. Now, the entropy measures disorder or randomness, or really the right way to think about it is that you are sampling more, you're able to sample more conformations, more configurations of the molecule. So one thing that can happen here is that you're losing configurational entropy. These are more flexible than this structure, so there are more ways of sampling rotations about bonds and angles here than here. This is a less constrained system. So these will likely lose some of the so-called configurational entropy when it forms part of a helix. So that would actually be a negative contribution to the binding. This, in terms of entropy, that might be favoring this. Now, on the other hand, water molecules can be hydrogen bonded to these functional groups here. Those water molecules have to get kicked out when these base pairs form. Now, that released water has gone from somewhat ordered configurations where it's tied up in a hydrogen bond to just the bulk water. So that would be actually more favorable in terms of entropy. So again, it's a very subtle balance of factors that one needs to keep in mind, and it's generally, certainly from structure, very hard to predict the relative contributions of these terms. But it's often done in papers, and it's important to try to think about it because one could go in and make hypotheses and models and then test them experimentally. Let's jump back to our statistical view of equilibrium. Okay, so here's our little reaction, A plus A goes to B. Simple unimolecular reaction. Delta G, the free energy of this process, is delta H minus T delta S. Okay, so we can think of a couple of different scenarios here. So here would be the population of molecules in given energy states. Okay, so the lower states are more populated. So let's think about a couple of cases. You can imagine that A and B both have equally spaced energy levels. The ground state here, first state here. The spacing is equal in both cases, but the ground state of B is just higher in energy by some amount. Okay, so equal spacings. Okay, then if we think about how these energies are filled up, which is shown by the darker bars here, okay, you can see that A is going to have more particles are going to be in A than in B. Okay, so A is going to be favored in this reaction, in this mixture. Okay, so some of B, there will be some of B will be populated, but mostly A. Now, on the other hand, so this would be a sort of example of an enthalpy or an enthalpy or internal energy, the way it's drawn here, an enthalpy-driven reaction. Now you can imagine a different scenario. Let's say we have the same offset. Okay, so B, ground state, is still the same higher energy state, but now B, whatever happened to molecule B, the spacings are different. Okay, the energy levels are more closely spaced. Okay, so now if we think about this population, there are actually more ways of populating B, okay? So this is an example where B would actually be, potentially could be favored, even though it's in higher internal energy. It may predominate in the reaction mixture because of this accessibility of states. This would be an entropically driven reaction. So again, when you think about what the meaning of these terms are, this is really how you have to think about the distribution of molecules over an ensemble.